Hi folks. I wanted to do a tutorial today to address something that a lot of people express some difficulty with, some confusion with, and at the very least there's a lot of interest in this, and this is dynamic fracturing. And so the idea in dynamic fracturing, normally when you do destruction, is that you pre-fracture your geometry. You take it, you break it into lots of pieces, you pass all those pieces into a dynamic simulation along with their constraints, and you just see what happens. You let it run through. In dynamic fracturing, you start with a single piece. So like this, and on the basis of impacts or other simulation events, you actually fracture it within the simulation. And so this lets you get lots and lots of fine pieces. It lets you get sort of recursive and hierarchical fracturing without having to sort of specify all of that in advance. So in this tutorial, we're going to cover this sort of process starting from scratch, and we're going to cover sort of how to do the fracturing, how to set up the simulation, how to get it back into its rest geometry. So you can see here, even as it fractures and all these new pieces are formed, we still know where they came from with respect to the original geometry. And then we're going to move into how to set up constraints and how to make those constraints follow that resting geometry, and how to make those constraints sort of behave and adapt to the simulation as it runs. Alright, so we're going to set this up pretty much completely from scratch. The only thing that I'm not going to build from scratch is just this little staircase here, and really this is the simplest thing in the world. I just have a single box and I've done a transform copy to build myself a staircase. So I'm just going to use this as kind of an interesting collision geometry, and that's pretty much all there is to those stairs. Everything else we're going to start completely from scratch. So I'm going to drop down a new geometry here. I'm going to call this dynamic fracture tutorial, and we'll dive right in. So the setup for this is actually pretty straightforward. Because we're doing almost everything inside of DOPs, we need almost nothing out at the SOPs level, but we do need some kind of an object to start with. So I'm just going to drop down a box. I need a little bit more space here, and actually I want my geometry as well. There we go. Okay, so I'm going to drop down a box. I'm going to make this a little bit bigger. Round 2 looks good to me. And I'm going to go ahead and just assemble this box. So I don't really need to do anything else. I'm going to let it have a name. I do want it to have a name, and I'm going to assemble it. And sure enough, that gives me sort of my nice initial box. It's sort of a single piece. We have our nice packed primitive. All of that is working nicely. And then I'll just drop a null here, and I'm going to call this geo. So this is my full SOP setup. Because we're doing everything else inside of DOPs, this is really all that we need. We just need an assembled piece to sort of start with here. I'm just going to put that in a little box, and I'll call it setup. So once we've got that, we just need a DOP network, and then we can start to get to work. We'll dive inside the DOP network, and let's just set up a very basic rigid body simulation. So we're going to want a ground plane, something to collide against. We're going to want some static geometry. This is going to be that staircase to collide against. We're going to want gravity on our simulation, and we're going to want that basic rigid body solver. And then finally we'll want a packed object, and that's where we're going to get our original geometry from. So I'll just wire this all together, run that all through, and now we've got our basic sort of bullet sim setup. I'll just start to drop this information in. So for our packed object, we're just going to point to that geometry we made. That's right there. That'll bring in this box. We're going to sort of reposition that, but let's get our staircase in first. So the staircase, I'm going to go back up to this top level geometry, those stairs that I had, and just grab this collider null, and that'll bring in those stairs. Now, before we get started, if we just look at the collisions for the stair, you'll see under bullet tab, if we visualize this, we just get this kind of single hull around the entire thing. Now the nice thing about this staircase though is that it's a bunch of separate boxes. So these boxes are actually sort of independent connected primitives. And that means that we can sort of check this box, create convex hull per set of connected primitives, and then we get a hull for each one of these steps. So if we turn off the geometry for a minute, you can see we get really nice collision here. So a staircase is a pretty nice, simple case for collision, and that's part of why I wanted to use that here. We can really easily just get a bunch of independent boxes. This is going to be pretty cheap to collide, but give us some nice geometry. Okay, so I'll just go back to display. I'm going to turn off the display of the ground plane because I generally don't like to see it. And then I'm going to sort of reposition this box to get us started. So if I go in here and I go to the initial state, let's just bring this up a bit. Oops, let's bring it back. That's going to be too far. And then we'll bring it up. And that's probably going to be a reasonable place to start. So if we play this now, our box falls, it bounces down the stairs. Perfect. All right, so we've got this set up. We have our basic sort of framework, and this is going to give us something to work with. And in particular, we've got a box, and it's bouncing around, and that means we're going to have impacts, and we're going to be able to read out those impacts and turn that into fracturing information. So to do this, if you've done my other tutorials, you'll probably be able to predict this next step. What we're going to do is we're going to drop down a SOP network, and we're going to do most of our work in here. So even though we're in a DOP network, we want to do most of our work kind of at the SOPs level. We're going to need to use that for our fracturing, so we want to be in a SOP network. So we're just going to make a subnetwork inside of the DOPS framework here. I'm going to call this fracture, and I'm just going to dive right inside, drop down to null, just to remind ourselves of what we're doing here. This is going to be our updated geometry. So I'll just call this geo updated. Then out here, I'm going to drop down a SOP solver, and I'm just going to wire that right into this post-solve input. And just a quick reminder, what this SOP solver is doing is it's going to replace geometry, this field here. So if you look down here, the data name geometry, it's going to show us that here as well. What this SOP solver would do is replace the geometry field on this object at the end of each pass through this solver. And so the geometry field is actually a little container here. So if we dive inside of our network here, if we open up our RBD packed object, you'll see we have this geometry container, and this is where we're holding our geometry. This is where this box is being held. So what we're doing with the SOP solver is we're basically saying at the end of each pass through the solver, replace this geometry with whatever we pass to it. And what we're going to pass to it is going to be whatever comes out of this SOP network. So we're going to use this external SOP flag here, and we're just going to dive into that network, fracture, and grab our geo updated. Now if we were to do this right away, because we're not supplying anything, what will happen is on the very first frame, this box will disappear because we're going to replace this geometry with nothing. So I'll just show you that. Sure enough, it's gone. So as soon as we hit frame 2, that box is gone because we've replaced the geometry with this null. There's nothing in there. So what we want to do instead is we want to basically take the existing geometry and then do something to it. And so to get the existing geometry, we're going to use a DOP import. And what a DOP import does is it basically fetches data from a DOP network. And the data that we want is this geometry here. So to do that, we can just go in here and drop a DOP import. And there's going to be a bunch of fields we want here, and in particular inside of a simulation there's a bunch of these fields we're going to want to sort of change from the defaults. So make sure you kind of follow along on all of these pieces. If you forget some of this, one of the easiest ways to do it is to go into your SOP solver and look at its default DOP geometry, because you'll see that there's all these various flags. So this would normally be ticked by default, this is different from default, this is different from default. There's all sorts of things, this is different from default. You can basically come in here and see what it does by default and see what these separate changes should be. But we can set this up from scratch. So the network we want, this is the DOP network we're interested in. That's just the one we're inside right now. So we're going to go .dot /. This is like Unix pathing. That's going to bring us up to the DOP level. We want the RBD object. I'm just going to sort of use star RBD star instead of remembering exactly what it's called. We actually want to fetch that geometry. And so already this is sort of resolving, it's not trying to transform anymore. But if we try to fetch it now, you'll see that we're not really getting anything. And part of that's we're on frame 2. So if we go back to frame 1, here we go. We've actually fetched our geometry. Now we do want to fix a few other things though. First of all, we want to get rid of this add DOP object path attribute. What this does is it basically, if we look in here, it's going to add this path attribute here, which is basically saying, hey, this is where I got this object from. By default, it already has a path, and this is where this packed fragment actually came from originally. Now this path is a lot more useful. This tells it where the geometry is coming from. This is telling us where we're importing from. And if you create this path object, it tends to confuse the bullet solver, and your geometry will basically vanish. It won't really know where to read it from anymore. So we're going to turn that off. And so you'll see we're just left with this path. And then the last few things we're going to do, we don't want to keep adding velocity to it. We're not going to add velocities because the geometry has its own velocity. So we don't want to take in the velocity of the container and add it to the geometry inside, our velocities are going to explode if we do that. So we want to set that to no point velocities because this geometry already has its own velocity. And finally, we want to hit do not trigger simulation. So normally we would be using a DOP import way back out here. So outside of our DOP-net, we would basically grab the data from inside. And in that case, if we're reading from it, we kind of want it to get the simulated data. When we're inside the DOP network and we're doing a SOP solver, what we're doing is I want to modify the data that I'm actually running. So this data here, I'm still going through this simulation pass. This post-solve is kind of part of this single step. So I don't want it to try to fetch the simulated data while it's simulating the data. I just want it to get sort of the data as it exists before doing anything. So we're going to toggle this do not trigger simulation, which basically says, go and get me the data. Don't try to finish this time step. Just go and get the data as it is right now. Okay, so with that done, we've got our box here. And if we were to just pipe this right into the GeoUpdated, now we'll just get our simulation behaving as it ought to before. You'll remember from the last tutorials if you've seen them. If you haven't, whenever you're working with SOP solvers, if you change anything inside them, just go and find some simulation object and make some change to it. I often like to just click this creation frame on and off, and that's just going to basically reset everything and make sure that it's ready to go again. So if we play this, everything behaves exactly as it did before we had that network, because all we're doing on this post solve is grabbing the existing geometry and passing it on through. Now what we want to do is basically say every time this box hits somewhere, we want to see, okay, how hard did it hit? If it hits hard enough, we want to fracture it. And then we want to have two pieces we're simulating and see if they strike anything, and if they do, we'll do the same check. So we need some extra information, not just the geometry, we need to know about its impacts. So to get impacts, what we use is another type of sort of fetch from the DOP network. And this is going to be a DOP import records. There's a few separate fields on here, but basically what we're doing, it's very similar. So the DOP import is like a glorified merge. This import is also like a glorified merge. It's basically just getting information from the DOP network. So we have some familiar fields here, like our DOP network, so we can set this stuff right away. We have our object mask, and then we have these data path and records and fields information here. What this is looking for is basically where is this information coming from and what records are we interested in. To find this out, we can go back up to our sort of DOP geometry spreadsheet, and we can look inside this RBD packed object. And if you look at the outset, there's actually no impact information. This information only exists when impacts are created. So if we step forward here and we wait for this block to hit, you'll see right on this frame, we get this new impacts entry here. So before the impact, there was nothing, and then as soon as we hit, we get this impacts entry. And if we look inside here, we have this impacts records. So this impact is basically the data path, and then this is the record we're interested in. And you can see this record has a whole bunch of fields. This is basically just stored as geometry. Now once that impact goes away, we lose it again. If we come forward until we hit another set of impacts, now we get some new impacts, and you can see these again. Now we only have a single impact, which I think is why it's showing us in this table format. If we move forward some more, we lose it again, we get more impacts, and so on and so forth. So what we're doing with this DOP import records is we're just fetching that impact information. So you remember the path was just impacts, and then the record was also called impacts. So if we do this, sure enough, we get that impact information. Now there's a lot of stuff in here. Some of it's more useful than others for our purposes. The things we're going to be most interested in are impulse, and that's basically the force of the hit. In addition to impulse, we're going to be interested in the object, the object ID. So that's the object that was hit, and this is always going to be the RBD packed object. And so this ID here, this number 2, you can also find by going into this spreadsheet, and it's just at the top level. So if you click any one of these objects, you'll see this object ID field. And this is basically read in the sort of ordering of the objects in the DOP network. So ground plane is going to be 0, static object is next if we go left to right, and that's going to be 1, and finally our RBD packed object is 2. If we were to reorder this, let's say we wanted to take our RBD and bring it to the front, now we'll see that its object ID, if we just refresh, is 0. So it's just going left to right through the network. Now, of course, we want our collisions to be going left to right here, so I'm going to move this back to where it belongs. We'll move the ground plane, and then the static object. And again, just refresh this. So our RBD packed object in this network is 2. It's not always going to be 2, but in this case it is. Now, just to keep that clear, I guess we have to step forward until we have some impacts again. Let's just move ourselves to some point where we get some impacts. There we go. So frame 21 is our first frame with impacts. Okay, so if we look in here, we can also find, I'm just going to show us all the attributes again. In addition to the object ID, we do get the object name. So if you don't want to try to remember this, you can also just get the name. Now, in addition to the object ID, obj ID, we also get other object ID. And this is the object that it's actually colliding against. So we know what object is colliding and what it's colliding against, and we know from impulse how hard it's hitting. Now, the last thing we're going to need to know, right now our RBD packed object only has one object in it. It just has that single box. Once it starts to fracture, we're going to have more and more of our pieces, but they're all still inside that same object, that RBD packed object. So the last piece of information we're going to need to figure out which piece has been hit is way over here, and that's primnum. So right now primnum is always 0, and that's because we only have the single object. Once we have multiple pieces, this primnum is going to tell us which of our pieces has been impacted. Now, 2 quick bits of information here. The impact records are going to give you primnum and ptnum, and if you've used VEX before, you're going to recognize those as being global variables, that if you use, say, a point wrangle, you're going to use ptnum to reference what point you're processing. And in fact, this data, this impact data, is stored on points. So if we want to process this impact data, we're probably going to go over points. That means that we're going to want to use ptnum, but ptnum is also specified as an attribute. So if we were to just do something simple, let's drop an attribute wrangle, and let's say, you know, I at pt equals at ptnum. I'm just writing something to basically try to access at ptnum. You'll see we get this little warning here. And what it says is the attribute is hiding global ptnum. And this is saying that the attribute on our record, ptnum, is actually hiding this global variable, so I can't use at ptnum to reference the point I'm processing. So this is a problem, and to deal with this, we're just going to rename those attributes. So I'm going to do attribute rename, and I only want to process 2 different things. I want to rename my ptnum to record pt, and I want to rename my primnum to record prm for prim. So if I do this, then I basically get rid of those 2 values that are like globals, because if I were to do a prim wrangle, then I would need primnum. If I were to do a point wrangle, I would need ptnum. I'm just sort of renaming those so they no longer collide. Now if I were to go here, you'll see that that warning goes away. Well, I got rid of the code. If I do that again, at ptnum, you'll see we don't have that warning anymore because we no longer have that conflicting variable. Okay. Now what we actually want to do is not so much this kind of processing. Instead, what we might want to do is filter some of these impacts. And this is totally optional. There's lots of different reasons you might want to filter them. The main reason I could think of, or I would think of, is maybe you only want these collisions to be processed if they're sort of impacting against certain objects. So let's say you had lots of different colliders. Maybe you only want them to fracture when they hit against certain colliders. Or maybe you don't want them to fracture when they bump into themselves. So maybe if OBJID and other OBJID were both 2, if they were both the same RBD packed object, maybe we wouldn't want to process those. For now, I'm actually going to leave all of these. I think basically any kind of impact is going to be valid for fracturing, as long as we're dealing with OBJID, as long as the initial object we're dealing with is this RBD packed object, we're going to go ahead and process that. Just for the sake of putting something in here, I'm just going to make sure, because we're drawing from this object, this OBJID should always be 2, but just in case something crazy happens, and just for the sake of sort of having some filtering so you can get the idea that, hey, we can pre-process our impacts, let's just do a quick check here. Let's say if OBJID does not equal 2, we'll go ahead and remove this point. And again, this should actually never happen in our case, but just to give you a sense of what you might do here to sort of pre-process some of your impacts. All right, so we've got our impacts and we've got our geometry coming through. The next thing we want to do is merge this information. We want some way to understand how these impacts relate to these objects. So I'm going to drop down an attribute wrangle. This is packed geometry, so these objects are points, so we're just going to do a point wrangle. And I'm going to pass in these impacts on this first input here. And what I want to do inside here, there's a few different ways you can approach this. You can see we have sort of several impact entries here, and they each have their own impulse. What I'm going to do is basically just pull out, for each sort of individual piece, what's the maximum impulse that's going to be hitting that piece. So we're going to go through all of the records that match, and we're just going to find the one with the maximum impulse, and we're going to store that value. So the first thing we need to do is find every impact that's relevant to this particular point we're processing. Again, this is sort of hard to understand right now because we only have one point, but again, imagine later where this is going to be fractured into multiple pieces. We want to check for each piece how many impacts are relevant to it, and then get the maximum impulse of those. So to find the records that are relevant to this object, we've already made sure that our object ID is 2, so all we really want to know is this record prim that we've recorded here. And we basically want to find for each individual point in this packed RBD, for each individual point / primitive packed fragment, we want to find how many of these impacts have the matching record prim. So to do that, we're going to use find attrib val. And so we could grab a single point by saying find attrib val, geometry stream 1, because it's this first input here. It's a point attribute because everything in these impacts, these are all point variables. And the attribute we renamed, record PRM. And we want to find points that match this attribute to the current PT num. And the reason here is that this PT num, as we're processing over points, we're going to go over prim 0, sorry, point 0, point 1, point 2. That's the same as prim 0, prim 1, prim 2, packed fragment 0, 1, 2, and so on. So we can just use the current PT num, and that's going to match up with that record primitive. It's going to give us the same object there. Now the problem with find attrib val is that it only gives you a single point. And if we have multiple impacts, and we do in this case, we have 3 of them, we want to get over sort of all of those. We want to iterate over all of them and find the maximum impulse. So the way to handle that is actually, there's a separate find attrib val function, and it's called find attrib val count. And this takes all the same fields, but instead of returning a point number, it's going to return how many fields there are. And what this allows us to do, how many matching entries. What this allows us to do is then iterate over those and pass that index as the last argument here to tell us which point to grab. And so we're going to do exactly that. We're going to do a for loop. So for int I, starting at 0, going up to count -1, and incrementing. Now we're going to grab our point, and we're going to use this index I, and we're going to loop over each of the impacts that matches. So that gives us the point, that gives us the value within the impacts to check. Now we just want to find sort of the maximum impulse. So to do that, we'll just keep track of a max impulse value, and we're just going to test in here. We're going to say if point impulse PT, so if the value for impulse for this particular record is greater than our current max impulse, then we're just going to set our current max impulse to be that value. So again, we're going to find all of the matching entries, we're going to iterate over them, and then each time we're just going to see is the current value for impulse greater than our sort of aggregate here, or our accumulated, our current maximum. If it's bigger, then we're going to reset our current maximum. So by the time this loop ends, this value will be storing the highest impulse we've found. So we just want to set that onto this point. So we'll just set an attribute with the same name. So now that I've done this, what we'll see is on this point geometry, we should have a new attribute called max impulse. There we go, max imp. And the value we're getting is 26,845. And if we go back to our entries here, you can see under impulse, 26,845 is in fact our highest value. So these two are lower values there. So that seems to be working. Now from here, the logic is actually pretty straightforward. What we've done is we've identified the maximum impulse on each piece. And so now, basically what we're going to do is we're going to separate this into two branches. We're going to say if the maximum impulse is higher than some certain amount, we're going to fracture that piece. Otherwise, we're going to do nothing. And then we're going to merge all that geometry back together to pass it through. So to give ourselves those branches, we're going to use the split node. Oops, didn't mean to dive in. And on the split node, we're just going to sort of test that max impulse. So we're going to define a group. We're going to say max imp greater than some value. Let's just say it's 100. And we're going to want to tell it that this is a point group because it doesn't really understand that. Now on this branch, we're going to do our fracturing. And on this branch, we're going to do nothing. And then at the end, we're going to merge these things back together. So this is going to be our basic logic. Now, right at this point, one thing I want to do, I don't like having these dangling values like this, so this is an explicit value here, 100, that I picked, and I'm deep inside. I'm in the DOP-net, I'm in this fracture subnet, I'm on a particular node here. I don't want to have these sort of arbitrary values being set and hidden inside these nodes. So I want to have this be a parameter I can access somewhere more conveniently. So I'm going to go right back up to my main geometry network here. I'm going to drop a new null, and I'm going to call this parameters. I'm going to set a special shape on here, even give it a color, just sort of identify this as being a different kind of a thing. And then I'm going to go in, and I'm going to, I went to this gear, and I went to edit parameter interface. I'm going to make a new floating point attribute, and I'm going to call this break impulse. So this will be the impulse we need to hit to trigger a fracture event. I'll just set that to the same value we had before, and then I'm going to copy this parameter, dive back into my fracture, go here, and paste relative references. Now you'll see that it's backticked inside this. This is telling it evaluate this and then turn it into a string. And that's often not what we want, but in this case, because it's a group expression, it is, because this group expression is itself a string. So if we resolve it, if we middle mouse here, you'll see that that resolves to the string 100. That gives us a whole string for this group expression, and that gets evaluated by this node. So this is what we want here. So now if we go through, what we've done is we've basically found this maximum impulse, and then we're splitting our geometry into two streams, and then merging it back together and passing it through. So if we went back and replayed this, everything should work the same way. We haven't done any fracturing yet, but just as a sanity check, everything should still simulate as it did before. And sure enough, it does. But what we have that's different now is if we go to our geometry, we'll be able to see over time, if we look at that max imp attribute, this now exists. And each time it hits somewhere, you'll see that we're actually bringing in this maximum impulse value. So our solver is doing something. We're just not actually doing anything different on those two branches yet. But we can see that the solver is working, and whenever we have impacts, we're getting that attribute coming through. Now our last step is going to be the fracturing itself. And it turns out if all you want is to fracture geometry, if you don't care about rest space, if you don't care about constraints, then we're almost done. This is actually very straightforward. So let's just show the most trivial version of all of this. So on our do fracture branch, the first thing we want to do is unpack this. So we're going to unpack this point. We're going to unpack this geometry here. I'm just going to skip forward to frame 21 again because that's where I know we had an impact. So we're going to unpack, and that's going to give us some geometry. And the reason we need to unpack is you can't fracture packed geometry. So packed geometry is represented by a single point. There's nothing to fracture there. So we need to unpack here. And one thing that people maybe don't realize about the assembly node and the assembly process and packed geometry is you don't need to treat it as a whole integral unit. So I always used to think, okay, I fractured my cube, I've got 20 pieces, that's packed geometry. Now I have that whole packed thing, like it's a single integral object. But actually you can pull out any one of those points anytime, do whatever you want to it, replace it with something else, add a new one. Assemble geometry, just think of it as points. And you can add points, you can take away points, you can do whatever you want. You don't have to process everything all at once. So what we can do here is we can identify just those pieces we want to fracture and only unpack those. We never have to unpack this side. Now that we're unpacked, we have our name attributes here, and of course we only have the one, but once we have more, we'll have multiple of these. And so what we want to do is for every point that's been identified, for every piece that's been identified, we want to do some fracturing. So we're going to use a for loop, and we're going to use each named primitive, because our primitives have names. This is all set up correctly by default. Our piece attribute here is name. We're going over primitives. That's all going to work nicely. And what we're going to do is we're going to do something in this loop, and then we're going to reassemble it. We're going to create packed geometry again, and we're not going to create a name attribute because we already have one, and we want to make sure that it respects the names that we have. So the basic process is we identify the pieces we want to fracture, we unpack them, we do something to each piece, and then we reassemble them and merge those back in. Let me just clean this up a little bit. Okay. Now before I get to the fracturing, I just want to address one extra problem that's going to come up here, and I can show it to you very easily. Let's just take a look at our geometry here. So right now, oops, I only have that one value. There we go. Right now we have only 1 point here. As soon as I step one frame, suddenly we have an extra point. And in fact, we keep getting these extra points for every frame here. And if we go over and look at the name, well, they all have this name piece 0. So what's going on here? Are we duplicating these pieces? What's happening? And the problem here is pretty easy to see. And this is that assemble will create something no matter what you pass into it. So we can just go over here. If I make a null and then I assemble that null and I ask it to create packed geometry, it's going to give me something. It's going to pack nothing into a piece of packed geometry, and it's going to call it piece 0. Now the reason this is a problem is because what we've done is we've split our branch into stuff to fracture and stuff not to fracture and then merge them back together. When there's nothing to fracture, this assemble node is still going to return at least 1 point. It's going to return this kind of a null point here. So every time there's no impacts to work with, we're getting this extra kind of ghost geometry being put back into our network, and that's what's causing problems here. So the way we can get around this is to basically say, we only want to do this whole process here, where we split into the stuff to fracture and the stuff not to fracture, then merge back together. We only want to do this entire network if there's anything on this branch. Otherwise, we just want to skip it and take the original geometry and do nothing at all. So the way to set this up is we can just use a switch. So we'll drop this switch down here, and what we want to do in this switch is basically ask how many points are in this. If there is at least 1 point, then we'll go ahead and do this branch, but if there's not, then we're just going to keep the original geometry. So we can ask that really easily. We can use the endpoints function, and we're just going to point to that doFracture node. And what we want to say is if endpoints is less than 1, then we're just going to keep the original geometry. So we'll just branch this off over here and feed it in through there. And now you can see by this dashed line and this solid line, what this is saying is, well, there's nothing in this branch. You can see that this is empty. So this value is less than 1, and that means we're just going to take the original geometry. If we go ahead and, let's just reset everything. If we go ahead and scroll over to frame 21 where we know there is an impact, and go see what's happening now, now you can see that this solid branch is over here. It's evaluating this side because this node has a single point in it. So as long as this node has at least 1 point in it, we're going to go ahead and do this entire side. Otherwise, we're just going to pass the original geometry. And now you can see if we go back out, we don't have, go back to our geometry container, we don't have any of that ghost geometry coming through. Everything's behaving correctly. So now the last thing we have to do is the actual fracturing. And this is just a handful of little nodes. Fracturing is every bit the same inside of this whole process as it would be outside. If you know how to pre-fracture, then you know how to fracture dynamically. You just need to know where to do that. And this is where we're doing it. So I'm going to do a very simple version. I'm just going to scatter 2 points. I'm basically going to say every time we fracture, I just want to fracture it into 2 pieces. So we're going to generate 2 points there. We're going to drop down a Voronoi fracture. We're going to take the original piece, and we're going to fracture it into those 2 pieces. Now the last thing I need to do, and don't worry about these error flags, the reason it's giving those is because there's nothing coming through here. We're giving it empty geometry, so it's complaining to us. We've already set it up so that this branch only executes when there is geometry here, so we don't need to worry about any of this. What we do want to worry about here is this default. When we produce the pieces and create those name attributes, the default is to overwrite, to create a new name. What we want to do is keep track of what we've done, and so we actually want to append. And what I like to do is just do a dash here, and what this will give us, if I skip over to 21 again, and go back to assembled, now we end up with piece 0-0 and 0-1 for the 2 pieces we've just created. So believe it or not, we've basically set up our dynamic fracturing. This will now work. So if we go back out, reset everything, and play, you should see when it hits, it breaks apart into multiple pieces. Alright, so this is all well and good. We're getting generally the kind of behavior we might want. We're able to get this to fracture into multiple pieces as it impacts. That's all looking pretty good, but there's some serious problems with this setup. We're having no issues with collision. We're getting all of our nice sort of pieces. Everything is behaving correctly physically. All of that is fine. The basic logic is working out. What we're going to run into issues with, though, especially once we start to try to get into constraints, is that every time we do this, we're kind of ruining our rest geometry. And what do I mean by that? Well, let me give you a simple example. Let's say I just give myself a new box here. I'm going to turn off everything else. I'm going to hide all those other objects. Okay, so we've just got this box here. If we assemble this box, create some packed geometry as we have been, if we look under primitives and we look at this packed full transform, you can see that when we assemble, this box is basically the identity matrix. So this matrix is a 4x4 matrix, so if we look at our first set of 4, the 1 is in the first place, our second set of 4, the 1 is in the second entry, and so on and so forth. What we really have is just the identity. And so what this is saying is when we assemble, our transform is stored as being sort of at rest, unchanged. If we apply any kind of transformation to packed geometry, so let's just add some transformations here, -2. This is totally arbitrary. We'll add some rotations. If I do this, you can see that the blocks moves and this primitive intrinsic updates. So this primitive intrinsic, this packed full transform, is basically storing everything we've done to this block. The upper 3x3 matrix is giving us the rotation matrix. This lower row here, this kind of bottom row of 3, is giving us our translation. You can see it's exactly those values there. And then our final row is, or our sort of last column, is going to be 0, 0, 0, and 1, and that's just giving us our scale. So our scale is basically sort of flat, and we're not going to be touching scale at all in this tutorial. Now, what this lets us do, this primitive intrinsic, means that we can take that value. So if I just go to, for example, let me unpack this. It's going to be a little bit long-winded, but just for the sake of argument, I can unpack this into its geometry again, and I can go back and basically take that primitive intrinsic. I can go and grab that. I can say matrix tr for transform, it's prim intrinsic from the first stream, and we just want to grab packed full transform, and we know there's only one piece there. It's the only piece we're dealing with, so it's number 0. And what I can do is multiply the position by that inverted transform. And if I do that, my box goes right back to where it is in its resting geometry. So the primitive intrinsic that gets stored here lets me understand where this thing came from. And this is really useful if we want to understand where things are sitting in their rest geometry, if we want to be able to recover the rest position of pieces even after they've been simulated. Now the problem comes in if I do something very simple. Let's say I just unpack and then reassemble. Every time you assemble, that default position becomes its resting position. So at the moment you assemble an object, its resting position, its transform, gets totally reset. What this means is that if we go back to our sort of whole simulation here, all of these pieces no longer know where they came from. And in fact, if we look at our primitive transforms, where are we? Packed full transform. You'll see these top few are at no change. So the last few that just got created are all sitting at the identity matrix. Basically, each of these pieces doesn't know where it originally came from. It doesn't know where it came from in this box. All it knows is where it was created, and it knows what it's done since then. So if we scroll through, you can see in sort of this top field all of these new reset entries. And so if we were to take this geometry, let's just delete all that. Let's just do a DOP import here, and let's bring that in. So let's just grab from this DOP network. I just did Alt drag. We'll grab that RVD object. We're going to grab its geometry. So if I do this, then I get all that nice geometry there. If I do this kind of a transform, and we need to do one extra thing here, we're just going to find the matching point. I'm going to use find attrib val, and I want to test that first stream, so I want to test the pack geometry. I want to check a point attribute called name, and I want to compare it against name. Now I'm doing this on points. These points don't have names, but I can deal with that by just promoting name here. So at this point, names are on the points. So in our pack geometry, our names are over here. They're on these points. If we just unpack by default without any transfers, it's going to get the original geometry, and that's where the names were on the primitives. If I transfer, basically anything I put in here, it'll say where is that on our pack geometry, and it'll put it in the same place here. So if I grab the names from the points and transfer, now I see them on the points, and I'll also find them on the primitives. So this just lets me know each point what piece is it coming from. So if I find that matching piece, I can then get the transform from that matching piece, match PT, and then invert those. And now we get something that's sort of box-like, but this is not the resting geometry. But this is what each point thinks is its resting geometry. So basically every piece has been put back where it was created instead of where it should initially be in the actual resting geometry. So this isn't what we want. If we want to know where the resting positions are, we need to deal with this sort of destruction of resting information every time we assemble. And so where that's happening is right here. So what we've done is we've found the pieces with high impact, we've unpacked them, fractured them, and then reassembled them. And as soon as we reassemble here, all of those pieces get a new reset transform. So to deal with that, what we're going to do is we're going to put these pieces back into their resting position before we fracture. We're going to assemble it there, and then we're going to retransform it back into its simulation space at the end. So we're going to need a little space for this. So I'm just going to kind of stretch all of this out. And what I'm going to do is I'm going to start on the points. So here we have, let me just scroll up to 21 where we know we get an impact. Okay, so here we have our point. And if we go to its primitive, we can see that it has an intrinsic. So something's happened to this box. Basically all that's happened is it's fallen down, so it's moved downwards. So we want to basically store this primitive intrinsic into an attribute that we can pass along and use later. So I'm just going to do a point wrangle, and I'm just going to say for at tr. So for at is basically I want a matrix. So just like we have f at for a floating point or v at for a vector, for at just says I want a 4x4 matrix. So I'm making an attribute, a 4x4 matrix attribute called tr for transform, and that's just going to be the prim intrinsic from this geometry stream called packed full transform transform, oh boy, packed full transform from the current primitive. So when we look at packed geometry, if you just look at its vertices here, you know, each one has 1 point. So primitive 0 is 0.0, 0.0, primitive 0. They're basically the same thing. They're just storing places in different spots on geometry. So if I'm processing 0.0, then I want the primitive intrinsic from prim0. So I can just use @ptnum in here. So once I've done that, now if we go over, you can see that we have a new attribute, and it's a 4x4 matrix. So it runs from 0 to 15. And that's going to be my packed full transform. So now when I unpack, I want to sort of propagate that information through. So I'm just going to transfer that attribute. So now that information, that 4x4 matrix, is sitting here on my points in my unpacked geometry. That means I can go in and I can just put that geometry back in its resting position. So I can multiply each point by that inverted matrix. So if I do that, you can see this block is here. This is before it's been moved. And if I show its resting position, there we go. And its resting position is down here at the origin. So you might have expected it would be sort of up there, but you'll remember that we packed this geometry at the origin over here. It only moved up to that higher position based on this transform here. And this transform gets applied to that primitive intrinsic, just the same as any other. So if I go back to here, and if I look at this last row, you can see 7, 10. That's that offset. So this primitive transform is always going to be relative to where we assembled it. So even things like these initial conditions are going to be respected and reflected in here. So let me just go back to 21 again. So here we go. We've basically taken, oh, it's confused at this point. We got to reset everything. Reset, simulate up to 21, please. And at 21, there we go. Oh, I know what's happening. It's because we've just changed this and put it in line. Now everything that propagates from here is a little bit broken. So let's just follow the logic. It's not going to work until we reset this because this is a loop. So this has been processed every time. But basically what we've done here is we put it back in its resting position. We're then going to fracture it in its resting space into 2 pieces here. And now we're going to assemble it, and this is going to turn it back into a single point, and we want to transfer those attributes again. So once assembled, we want that, that translation to be in here again. I'm going to have to come back through here once we've sort of re-updated everything to show you how this propagates through, because right now it's unhappy because I'm only doing part of these steps, and so none of this is caching correctly. So just bear with me for a minute. What we've done is put it in resting space, we fractured it in resting space, and then repacked it. So as we've seen before, as soon as we repack it, its transform is going to be set, if we go to the primitive transform here, it's going to be set back to the identity matrix. Now primitive attributes, some of them can be set. You can just say, hey, change this attribute for me please, and just pass it a new variable. Packed full transform can't be. It's completely inaccessible. You can read it, but you can't write to it. It gets written by all the other things that you can do. What you can do instead, though, is use a little function called packed transform. And this lets you transform packed geometry. This lets you basically apply transformations to packed geometry. So Houdini doesn't like you trying to set packed full transform yourself, just writing numbers in there as you choose. But you can still tell it to transform that geometry, and it will respect all of that. So we want to pass it, and I always forget exactly the arguments here. It's this first geometry stream, and actually we might not even want the geometry stream. I never remember exactly how to do this. I think we just want to pass it the point, and then we want to pass it that transform. Okay, no, it doesn't like that. What arguments do you want? You want an integer and a matrix. Okay. Oh, I see. I gave it an integer and a matrix. It wanted, yeah, it does want the geometry. I don't know why I thought it wouldn't. There we go. Okay. So what we're doing here is we're saying set on this geometry stream this primitive, and we're just using ptnum because again it's assembled geometry. It's the same thing. The points and the prim numbers are identical, and we just want to give it that transform. And this transform here is the same one we passed all the way along that we initially extracted. So what we've done is we extracted its current transform in the simulation, we undid that transform, fractured at rest, reassembled, now we reapply that transform. And so by the time we've hit here, we're back in that original simulation space. So let's just put that back in this merge here. And now, whoops, I don't want that. Now if we reset everything, we should get everything behaving nicely. We have this extra box. I suspect this is illusory. Sometimes Houdini, when you're dealing with sort of complicated loops and things, the update display, this display here, will get confused. You can fix this by just making a new scene view. Get rid of the old one. If we scroll up here, you can see that that box is gone. So that box didn't belong there. It was just getting displayed because it forgot what it was supposed to display and what it wasn't. So you can see here that this all behaves nicely now. And if we take this, the other thing you can see is that if we watch the top here, none of these new things are being put back at the identity matrix. They're all keeping their old, earlier primitive intrinsics. And so if we go back out here now, and we do this import, here's all our fractured pieces. If we do this retransform, you can see everything is sitting back in its resting positions. And the normals are a little bit borked here, but that's not really a big deal. We can fix that very easily. The key thing is that all of these pieces now remember where they came from in the original box. So whereas before they were all scattered all over, they just remembered where they were created. Now, by doing that sort of remove the transform, fracture at rest, and then reapply the transform, now each of these pieces simulates correctly. It all sits where we want it in the simulation, but we also know where it came from in the original rest geometry. And this is going to be absolutely critical when we get into constraints. I do want to do one extra thing before we get into constraints here though, and that's going to be something to make sure that this system never kind of breaks down. And the way sort of it might break down is right now we're allowing it to fracture anything. So if I give myself an exploded view here, let's just really burst this out. I'm going to put some normals on it so they look a little bit nicer. There we go. You can see that so far we're doing okay. All these pieces are reasonable, but we are starting to get some pretty small chunks here. And you can imagine the longer this goes, and in particular the lower we set this impact threshold, so maybe if I set this down to basically nothing, if I reset the simulation here, so let it play for a minute, you can see it's fracturing apart, and you can see we're starting to get some very small pieces. So if we kind of zoom around through here, we're getting some pretty small little chunks showing up. And again, so far these are all pretty okay, but the issue is as we get smaller and smaller, we're going to keep trying to fracture these pieces. So if I cut this piece apart and then cut it again and again and again, eventually I'm going to get a really, really tiny piece. And there comes to be a point where either you're going to break the Voronoi fracture, it's going to be upset with the size of your geometry, or you're going to break your simulation. It's just going to be confused by having really big pieces and really, really tiny pieces. And I've had simulations just not function because there was one overly tiny piece that just broke everything. So what we want to do is make sure that we don't fracture pieces beyond a certain limit. This is going to save us computation, it's going to save us simulation headaches, and frankly, by the time we get down to these really, really small sizes, you're going to want to just spawn points and then instance some geometry on there. You don't really want to simulate those tiny, tiny bits of dust and debris. So the last thing I want to do before we get to adding constraints is basically put a limit on the size that we'll fracture. And so the first thing we can do here is actually just do a little bit of visualization, because we want to sort of say, well, what is the smallest piece I want to fracture? So the way I'm going to do this, I'm going to use a measure SOP here. I'm going to measure volume, and I'm going to accumulate per piece. And my pieces have names. It's not a class, it's name. So our pieces are already named. And so this is just going to measure the volume of each piece. And so you can see each piece here gets its own volume. Now what I want to do is just make myself a little visualization. So let's say our default color will just be white, but we're going to say if, yeah, I'm going to put this on primitives here. Okay, if our volume is less than some threshold that we can kind of toggle and play with here. If our volume is less than some threshold, let's just color it a different color here, just so we can see. We'll color that red. So right now nothing will get colored because our threshold is not initialized. So I'll just hit this button here. And if we set this somewhere pretty high, we'll see that everything is above that volume. If we start to sort of scroll this down and down and down, you'll see the bigger pieces are okay. And what I want to do, I'll maybe re-explode this. So you can see now we're still picking out sort of most of these pieces. We can just keep dropping this threshold until we decide, okay, yeah, maybe this is the smallest that I want it to be, and then at this point I don't want it to fracture anymore. So where you choose to put this is a little bit arbitrary. I think this is probably pretty good for our current purposes. If we wanted to get smaller than this, you know, some of these are still looking a little big. Maybe we can 0.001. I don't know, I'll leave that at 0.002. So let's say this is going to be our threshold. You can choose kind of whatever number you like. The basic idea is we just want to make sure we're not trying to fracture pieces that are already so small that the stuff we'll end up with is going to be simulation breakingly small. So this threshold here, all I've done down here, this is just really for visualization purposes. So this threshold here we're going to want to apply somewhere. So the first thing I'm going to do is go up to my parameters and set a threshold here that we can reference somewhere. So I'm going to add a new parameter here, floating point. I'm going to call this min frac vol for minimum fracture volume. Apply, accept, and I'm going to set that to that value we just determined that there, 0.002. And we decided that was okay. So this is going to be my minimum fracture volume. Now I would like to use this somewhere. And what we're going to do is back inside this fracture logic, we're going to go into this loop here. And what we want to say is basically, if the piece we're processing is too small, don't do this. And so that's easy enough. We'll just take this piece. We're going to do that same measure. We're going to measure volume, and we're just going to say throughout. We're already looping over pieces. We don't need to go sort of per piece. We can just go throughout the entire geometry because we're only going to get one piece at a time. So we measured that. These volume values are going to be sitting on the primitive. Right now it's complaining because there's no volume, no pieces to process, but basically this will be sitting on the primitive. So I'm going to promote that. We're going to go from primitive to detail. The attribute is volume, and we just want to grab the first match. It's going to be the same value on every primitive, so we don't need to do anything fancy like the average or the maximum. Let's just find the first match. That's going to be the computationally cheapest version. I'm going to drop a null, and this null is just going to be called volume measure. And the reason I've got this here is because we can now reference this detail attribute we've just made here and check what it is. And we'll do this in a switch. We'll grab a switch, and we're going to say if the detail of this volume measure node we just made, the detail attribute called volume, and the first component of that is just one number, so it only has one component, but we need to specify that anyway. So if this volume measure is greater than, and hopefully I still have this paste relative preference, sure enough, if it's greater than that channel we created, min fracture volume, then we'll do this branch over here. Otherwise, we're just going to pass through uninterrupted. So I'll just grab this and pipe that through. So now what we're saying is if our piece is too small, then we're just not going to do anything to it. But if it's big enough, then we'll do this fracture over on this branch and pass that through. In both cases, we're not going to run into that situation where we're assembling a null. The only thing that's going to change is we're going to unpack the geometry and then repack it without changing it, or we're going to unpack it and then fracture it and then repack those two pieces. So in both cases, we're still passing something through, so we don't have to worry about those ghost pieces. That's still being handled by this switch here. So if we do this, we're not really going to see any major changes to our simulation here. All we've done is ensure that we're not going to get overly small pieces. Now, it is running more slowly, you'll notice. And the reason for that is it now has to process volume on every step. And that's not the cheapest implementation, that's not the cheapest thing it's doing. So that is going to be a little bit slower. There's one other reason we're seeing this slowdown though, and that reason is very similar to this packed intrinsic, and we're going to see some other aspects of this in a minute, but I'll just show you this one. Another thing that happens when we create a new piece is if you look on the bullet, we have these fields. We have orientation, we have pivot, we have rest, we have velocity, and we have angular velocity, W. If we just look at velocity in particular here, you'll see as soon as we hit on frame 21 here, our new pieces no longer have any velocity. So every time we hit, we're basically getting rid of the velocity that we had in those existing pieces. So each time we create new pieces, they're losing that velocity information. And especially because we set this value so low, basically as soon as anything even brushes against something else, it fractures and it loses velocity. So that's why we were seeing it sort of stalling. So first I'm going to put this back up a little bit. That should speed things up a little bit. But what we also want to do is basically bring that volume or that velocity through. And we can do that very easily. All we want to do is go here where we unpacked. And in the same way we brought over our transform, which is a point attribute, our velocity is a point attribute. It's sitting on each of these packed primitives. So when we unpack, we can just maintain that velocity. We'll just carry it through. We'll do all of this stuff. That velocity will remain unchanged by all of this. It'll propagate through. And then when we reassemble, we'll just put it back onto the points. So if we do this, go back through again, you'll see first it's a lot faster because we're not sort of shattering everything at that tiny, tiny impulse. So that impulse of 1 was just way too low as the threshold. 100 is a lot better. But we're also seeing it's got a lot more energy. And this is because if we go back to our first collision here and over to velocity, you'll see we have this sort of large velocity component. It's moving mostly down. As soon as we step to here, that velocity is maintained. We're seeing this, it's not looking like the same velocity because we've already gone through sort of the entire network again. But we are maintaining that velocity that we had before. And this is letting the whole thing kind of behave correctly. It's giving it more of that dynamism, it's letting it sort of bounce and interact. So what we've got so far is some fracturing here, and this is all behaving nicely. But the last thing we might want to do is allow these pieces to be sort of bound together. So even though they start to fracture, we might want them to kind of hang together for a bit. We might want some constraints here. And we're part of the way to getting this set up nicely because we've got this nicely well-behaved rest geometry here. So even as it fractures, we know where each of these pieces should be relative to each other at rest. So this is going to be really critical. So let's dive back into our DOP network. And we're going to have to do a fair amount. Let me get this back to nice flat shaded. I'll get flat wire shaded. We see a little bit more. So we're going to have to set up a few new things in this DOP network here to make this all work. And of course, the first thing we're going to need is a constraint network, because if we look right here, we don't have any constraints at all. So we'll just drop in a regular constraint network here. That's not it. Constraint network. We'll drop that right in there. And we don't need to specify any SOP path. It's starting empty, so we can just leave it empty to begin with. And then we're going to define a glue constraint. So we're just going to do our simplest possible constraint, which is glue. Pipe that right in there, and call this glue. And to begin with, I'm actually going to set the strength to -1. And if you set glue to -1, it will never break. It's completely unbreakable. So what we're going to do is we're basically going to bind all these pieces together. So they're going to tumble down, but the box will stay totally intact. And that's how we'll start, and then we'll work out from there. Now, the other thing I want to do with these constraints is something that's a little bit different than what I've shown in previous tutorials. So if I just rename this for a second, I'll just call it CNET. So you might remember, or you might know already, constraints are found by default under this Relationships tab. And so we can go to Relationships, CNET, which is the name of this constraint network here, constraint network, and finally we hit our geometry, which is of course empty because we didn't specify anything. But this is where all of our primitives, all of our constraints would be. Now, by default, these are specified at the relationship level. And what this lets you do is define constraints between objects. So if I had sort of two different RBD packed objects, I could have constraints between those separate objects using this type of a constraint network. However, The downside to this is that when your constraint network is defined at the relationship level, if you want to modify those, you have to pipe a SOP solver into this input here on the constraint network, and it will always be evaluated at the beginning of the time step. If you want to update your constraints later on, if you want to update them sort of over here at the post solve, for example, or somewhere else in this flow, you can't do that when they're defined at the relationship level. Fortunately, what you can do is if you go under the relationship tab here, there's this little toggle that says attach internal constraints to object. And if you hover over it, it'll give you some more detail. But the gist of it is that if your constraints are only between pieces of the same object, and that's our case, all of our chunks are within this RBD packed object. So everything is with respect to a single object. If that's the case, then you can get some advantages by basically moving those constraints inside this object. And then they'll move around with that object, they'll only be with respect to that object, and the really good side about that is you can now solve them and modify them wherever you like in this flow with the same flexibility as solving the rest of the geometry. So when we hit that toggle, what you'll see over here in the RBD packed object is now we have a new container here. It's called constraint geometry. So now, if I untoggle that, you'll see it goes away. If we're at the relationship level, we find it under here, under CNET, constraint network, geometry, we find it sort of tucked away here. If we just put it on the object, we just get an extra geometry container here. And this is where our constraints will be held. So that's pretty handy, and that means we can put our solver anywhere we like, and we're going to want to do basically that. Now, this idea of attaching extra geometry containers raises the next point that I'm going to sort of bring up here. And before I get to that, let me just show you conceptually what we'll be doing here. So now that I have, oops, that's not what I want another SOP solver. Now that I have this extra container here, this constraint geometry container, what I can do is use these SOP solvers in exactly the same way as before and point them to this container. So this SOP solver here is updating geometry. You can see that's the data name specified here. And so whatever sort of SOP is output and specified for this SOP solver, so that's currently this external SOP, that gets copied into the geometry container. If I have another SOP here, and I just say, well, instead of using the geometry container, use the constraint geometry container, now whatever output goes into this SOP solver, that's going to get piped into and replace this geometry. So by having multiple containers, we can specify solvers that are particular to specific types of geometry, specific geometry containers. And so here we can just update our geometry in one solver and our constraint geometry in another solver and do them both in this post-solve time step. Now, one thing that will come up from this though, if we look at the basic logic out here, let me just sort of, I'm just going to illustrate this with nulls just so we can see it more cleanly. We're going to grab our geometry, that's our DOP import. We're going to do something to it. We're going to process it. That's our fracturing. And then we're going to have our updated geometry. And then we're going to do something with that. Oh, sorry. I just want this to be a null. I just want to kind of illustrate the flow. Process more. And we're going to use that with some other information and get our updated constraints. Now, the issue here is that what we're doing in this network is we're getting our geometry. So when we evaluate this solver to update our geometry container, we're going to go through up to this point. We're going to grab our geometry from that same container, we're going to process it and then put it back into that container. We get to this solver now, and it wants this output. So I don't know, honestly, to what extent DOP retains the state of these sort of internal subnets. And so what I do here is maybe not necessary, but it is safe, because the concern that I have, and an issue that might come up, hypothetically, is that we solve this, we grab our existing geometry, process it, put it back into that geometry. Now when we solve this, it's evaluating the SOP network again. And so it's grabbing now potentially that updated geometry, doing this process, and then using that process to update the constraints. So in effect, there's a risk that you're looping through the geometry more often than you want to be. and you might be using the updated geometry from here when you process it through to get to the updated constraints. So the way I like to sort of get around that, or at least ensure myself and sort of give myself peace of mind at night that this isn't going to happen, is to actually define another geometry container that just holds a copy of the geometry. And so the basic logic will be every time we step through, we're going to copy this geometry container, our main geometry container, and we're going to do the work in both of these solvers within this fracture softnet. We're going to do that work on the basis of that copy. That means when we process through the first time, we're going to have grabbed the copy and we're going to update our geometry container. And then when we go through and update our constraints, we're still just starting from that copy. So no matter what, even if it knows not to bother recooking all of this and it just proceeds from there, that's the optimal solution, then no harm, no foul. If it does sort of lose the fact that it's cooked this, or it doesn't sort of flag this as having been already run by the time it gets to this second update, then we're still okay because we're starting from that same initial geometry. We're not starting from the updated geometry, we're still just going to use that copy. So let me show you how you can set that up. I'm going to put down a node that you've probably never used before, but maybe you have, and this is the apply data node. Now, an object in DOPs holds all sorts of different information, and we've already seen basically this constraint network is applying some information. It's adding new constraint geometry. This gravity node is applying these forces here, these gravity forces. Here's that gravity force. All of these nodes that pipe through along this gray line are essentially applying data. We don't think of it in those terms, or we don't use that language all that often. We say, oh, we're adding a force, we're adding a solver, we're adding constraints, but really we're just adding generically, we're adding data. We're just putting things onto that object. So apply data just makes that more explicit and says, well, hey, whatever you want to add to this, go ahead. And what we're going to add is just some soft geometry. And what we can do here is we can give this whatever name we like. So this geometry, I'm going to call it geo_copy. And so when I do this, you can see over here, let me collapse those forces again. Now we have this other new container, geo_copy. And right now it's empty. But what we're going to do with this is before we get to any of these solvers, I'm going to drop down one more SOP solver. I'm going to put this right at the front. And this one is going to update geo_copy. And what we're going to do is we're going to grab, let me resolve these things, this is all fine. We're not going to grab geo_copy here. We're going to grab geometry. And so what we're going to do, just in this solver, this is the most simple solver in the world, all we're doing is we're grabbing the geometry container and we're copying that into geo_copy. So now geo_copy holds the state of the geometry right before we start, basically at the beginning of this post-solve time step. Now what we can do is use that geo_copy in Fracture instead of using geometry. That means this solver will update on the basis of this state, and this solver will update on the basis of this state. So we don't have to worry about this solver operating on this updated geometry after this one. It's all just going to update on the basis of this copy, and this copy won't change again until we hit this solver again on the next time step. And so the last thing we need to do for that to work is go back in here, and what we're really changing is this grab geo part, and so that's this DOP import here. And so right now what we're doing is we're grabbing for the RBD object, that's all fine. By default, this geometry data path is going to be geometry. We want it to be geo_copy. Now there's one extra thing we have to do that's a little bit esoteric. These transform flags transform geometry with position data and with geometry data. This information is sort of, you can think of this as being sort of relevant to the container or relative to the container. And functionally what's happening here, because we have this geo_copy, and it has, in a sense, its own kind of transform for the container for the whole simulation, because we're copying the geometry into there, if we then pull that transform out at the same time, we're basically just adding the geometry multiple times. This is similar to how we don't want point velocities. Basically the points already exist on it, so if we add the point velocities again, we're basically just we're like duplicating everything. If we keep these transform flags on, what we're going to get is we're going to pull in this geometry doubly offset. So that sounds crazy. Let me just go right to frame 2 here before I turn those off. And you can see what I mean. So here we have our geometry copy, and it's way up here. And you can see that that offset is double the offset of the actual geometry. So the real geometry is sitting here. If we bring it in, if we DOP import it and we keep that transform, we're basically adding that transform twice because this geometry is already transformed because it copied that. If you don't quite get this, just kind of take my word for it. Having those flags is doubling your transform, and you don't want that. So now that we're grabbing the copy, we're just going to turn off these two flags here. Now otherwise, now that we've set up all of this, if we go ahead and run this, it should look the same. Everything fractures and falls down, and that's all great. Perfect. So now we've just added some extra information. Now, one more bit of housekeeping that we're going to need before we get into our constraints, and it's another thing that I have a really hard time explaining because, frankly, I don't understand why it works this way. In a default bullet simulation, every item has its own unique ID. So you can find this under ID. Here we go. Each of these objects has its own ID. That's great. When you add a new object, what happens is it initially sets it as ID -1. And that's really important. Let me see if I can find any of those. I'm in the copy. Let me go to geometry. Geometry will have some new IDs. Here we go. So all the new objects start with ID -1. And this is important because an object with ID -1, that tells the bullet solver it's new. And the bullet solver has to do some things to new geometry before it can sort of process it. And in particular, one of the most important things is define its collision geometry. So a brand new object, bullet solver doesn't know what shape it is. It doesn't know what kind of collision it has. So every time you fracture a new piece, bullet has to recalculate that stuff. And the way it knows to do that is because it has no ID. And so if you look on the detail, you can see the next ID is already set up. It basically keeps track of, okay, what's the highest object I've dealt with so far? I've got some new ones. I'll start labeling them from there. So for whatever reason, if you do not have constraints in your network, this alone is enough. This fact that the new objects start at, where's my ID? New objects start with an index -1 or with an ID -1. This is fine. You don't have to change any of the old objects. As long as the new objects start with -1, everything will work fine. For some reason, and I don't know what the reason is, but once you start to add constraints into this network, this alone won't be enough. What you have to do instead is reset every object. Both the old ones and the new ones. They all have to be reset on every time step. If you don't do that, you'll start to see them slipping through collision volumes. They'll collide and interlap with themselves or overlap with themselves. They'll start to fall through the ground plane. Basically, your collision geometry just won't function. And again, I don't know exactly why this is, but I do know that it's pretty easy to fix. And what we can do is just add another SOP solver. And this is going to be updating geometry. And we're going to put this in the pre-solve. And I'm just going to call this reinitialize. And all we're going to do in here is we're going to drop an attribute wrangle, a point wrangle, and we're just going to say set the ID for every piece to -1. Just reset everything. And so what this means is every time we pass through this network, the very first thing we're going to do is we're going to tell bullet, hey, all of these pieces are new. I need you to recalculate all of their collision geometry. Now that's a little bit expensive. It's kind of computationally expensive, but as far as I can tell, it seems to be necessary, and this is the only way I've found to avoid that kind of collision issue. So if you just throw this on here, what you'll see if you run this again now, if we just even move over to here, actually let me just grab ID, and I'll grab the copy where it's updated. You can see that this single piece is getting a new ID every frame. It's basically being incremented. So every time we pass through, every piece is getting new IDs. So you can see that they start to get really, really high very quickly. Fortunately, ID can be very, very high. And for a sort of rigid simulation like this, you're not really going to have to worry about this topping out. Consider the fact that you can have a pop network or a flip network with millions and millions of points, and those each get unique IDs. You're pretty much fine here. Unless you're running sort of tens of thousands of frames, you're never really going to run into an issue. So this is a bit of sort of computational overhead. It's a little bit obnoxious, but it's the only way I've found to safely make sure that your collision geometry is updating on every frame, and it's all sort of going to behave correctly. Okay, so now that we've got all of that set up, we can actually start looking at solving this constraint geometry. And I'll warn you ahead, this is going to have a lot of VEX and a lot of little steps and bits and pieces, but I'll try to work through it as sort of cleanly as I can here. So what we're going to want to do is, first of all, we need a little bit of information, so a little bit of extra information about the new stuff that we've done here. In particular, we're going to want to know which pieces are new, and we're going to want to keep track of what their old name was, their name before being transformed or before being fractured was. So the first thing we're going to do is just set up some of this extra information. So I'm going to go here before we do anything, and I'm going to drop down a primitive wrangle, a prim wrangle, there we go. And I'm just going to say string old name is current name. So we're just going to copy the current name into a new string attribute. So now we have name and old name. Just going to pass that through here. And then the next thing I want is after fracturing, once we fracture here, I want these pieces to be in their own group. I want a new group for these pieces. I basically want to identify anything that I've just fractured here. And I'm going to put this group on points for now, and I'm going to call it new piece. So now we've got this group called new piece, and that's going to basically tell us, okay, these points are new ones. So now to make sure I have that information accessible, once we've assembled, we want to make sure that we transfer that over. So right now we're transferring this transform and the velocity. I want to, in addition, transfer old name. We're already going to get name because by default assemble is going to keep name. I want to transfer old name as well, and I want to transfer that group, new piece. Okay. So now if we come through here, and I just want to reset this so we can actually look at some geometry there instead of that sort of broken cache. So let's just go to, I think, there we go. 22 seems to be the first frame where we, oh, I'm looking at copy. 21 is where we first get that fracture. Okay. So if we look here, the first thing we notice is we still have this transform. We're going to want to clean some of the stuff out. I'm actually just going to go ahead and drop an attribute delete, because we don't really want to carry this whole 4x4 matrix. That's a really big, heavy piece of data to have on every single point. We don't really need it. We needed it to do this processing here, but we don't need it anymore. So I'm going to throw that in there. So now you can see that we have name, and we have our velocity, and we have our position, and we have that group new piece. But what happened to old name? Well, old name was on primitives before. And so here, where are we? It's also on primitives, so it's sitting there on primitives. So whenever you do this kind of transfer, and this is for both unpacking and assembling, it's just going to put it in the same place it was before. So to get this onto points, I'm just going to do an attribute promote. And I'm going to move old name from the primitive to the point. So now if we look at our points, we have our position, our name, our old name, our velocity, and this group, which is telling us that these are new pieces. So that should set us up to make sure that our geometry has all the information we want for adding these constraints. Now the last thing I need to do, just to make sure everything is well behaved, is address the fact that this group, this new piece, right now, if we think about all the logic that we have everywhere throughout the whole program, new piece is only ever being set. It's only ever being added to these new pieces. We only really want to know about the new pieces on this current pass. We don't care about pieces that were new from previous passes. We just care about ones that are new right now. That means we need to set this back to 0 somewhere. And the most natural place to do that is right here in this reinitialization. So right at the pre-solve, before we do anything else, in the same loop that we say, okay, let's set ID to -1 so it updates the collision values, let's also go ahead and say this group new piece, it should just be 0. So when we start each pass through the simulation, we want to say, well, nothing is new. Only tell me about new things that are new within this time step. Okay, so let's refresh based on that. Really, we're just carrying information through. Bring ourselves back to 21 here, and dive back into this solver. So at this point, let me get rid of these. I had these comments before for what we're going to do with these constraints. We're just going to talk it through. So if we get down to here, here's our updated geometry. It's sitting up there, and we have two pieces. if I get flat wire shaded, it's assembled, so it's not going to show me those boundaries. But we've got our two pieces, and we can see we've got name and old name, so they both came from piece 0, but it's piece 0, 0 and 0, 1 now. And we can see that they're both in the group new piece. So that's all the information that I need to be sort of putting my constraints together. Now the logic for our constraints is we want to take some mixture of new constraints based on what the geometry is like now after fracturing, and our old constraints, and we want to kind of combine those things together in an intelligent way. So let's just start with our old constraints. Now the first thing you might expect is, well, we're probably going to use one of these DOP imports, and we're probably going to grab it from our current DOP network here. We're going to use this RVD object. We're going to fetch our geometry. And instead of using the geometry path, we're probably going to want to use that constraint geometry path. Now we're going to sort of want these same things. Don't trigger simulation, don't add any point velocities, don't give me this path attribute, and we also don't want to transform this stuff, because these constraints, we're going to be creating them in their rest space, and then they're going to be sort of moving along with the geometry potentially. We don't want to use that geometry information. We just want them back at their rest space. So this is going to pull in our constraint geometry. However, if we try to run this right at the beginning, it's going to be upset with us because there's nothing in here. It's going to be sort of it's going to be sort of unhappy with us because this doesn't exist on that first frame. So what we'll also do is just add a little empty set here, and what we're going to say is if the frame is 1, then we'll grab that null. And otherwise we'll just grab, we'll import. So we're not going to try to import on that first frame because nothing exists here yet. So on the first frame we'll just grab it from an empty null. So this is a little bit obnoxious, but it does just keep things sort of from erroring out because it's trying to access things that don't exist. Now I'm just going to go ahead and delete anything that's broken. This is a group that the solver will produce for us. So glue constraints can break. They'll break whenever the force on them is stronger than their strength. So we're going to potentially, right now, you might remember we set glue to be strength -1, so it's never going to break. But if we had this different strengths, it might eventually break. We want the solver to be able to handle that stuff, but we don't want to look at those constraints right now. So instead of keeping them in a broken group that we might process differently, for now I'm just going to delete these entirely. You might not want to do this if you're doing it in different approaches, but this is what I'm going to do here. So we're just going to start and we're going to delete these entirely. Now the next thing I want to do is I want to sort of remove any constraints from the old geometry that refers to names that don't exist anymore. So for example, if I had a constraint between piece 0 and piece 1, and in my new geometry I have piece 0, 1, 0, I have piece 0, 0, piece 0, 1, and piece 1, I no longer have a constraint. I no longer have the objects piece 0 and piece 1. I only have piece 1 now. So basically I want to check for any constraint that has sort of objects that don't exist anymore, and I'm just going to get rid of those constraints. Now this isn't too hard. We're just going to drop down an attribute wrangle here, and we're going to run this over primitives, and we're going to be referencing our updated geometry, because this has all the names of the geometry that does exist now, and this is going to be sort of asking, do the names in my constraints still exist? So first we're going to get the points. We'll get point 0, and we're just going to use prim point. It's just going to grab the points from the primitive. So we're going to specify our current primitive that we're processing, and we want point 0, and prim point at primnum 1. We don't care about the order. We know there's only 2 points in any given constraint, so constraints only have 2 points. We don't really have to worry about any error checking or number checking or ordering or vertex order. None of that matters. We can just grab 0 and 1. We don't really care about anything else. So we don't really have to worry about any of that vertex order stuff here. We're just going to grab the names from those points. So again, from the current geometry, we're going to grab name of point 0 and name of point 1. Oops. And then what we want to do is figure out if both of these names still exist. And we can do that using our old friend findAttribVal. And basically what we're going to do is we're going to look for this name in this geometry. If it doesn't exist, findAttribVal will return -1. It'll basically say, well, there is no point index that satisfies that. So all we need to do here is basically ask if findAttribVal 1, we're looking at that sort of second geometry input. It's a point attribute, the attribute is name, and we want to compare it to name 0. If that is -1, or, again, findAttribVal 1 point name 1 equals -1. So if either of these things are missing, we're going to remove this primitive at prim num, and we're going to delete the points associated with it. So that's what this 1 means. If you set this to 0, it would remove the primitive but not the points. Setting it to 1, it will remove everything. Okay, so this is the processing we need to do for the old constraints. This is basically just saying get rid of the broken ones and get rid of any that basically they reference something that doesn't exist anymore. So this is the easy branch. We're going to merge this in with some new constraints, and this second branch gets a little bit more complicated. So the first thing we want to do is take this geometry. Let's see if it actually... I'm going to go ahead and refresh everything because I want to be able to see my geometry here. I at least want to have something I can work with. So sometimes with these SOP solvers you have to just keep refreshing to get your geometry back. Okay. Well, it looks like it doesn't want to show it to me. It is invisible right now. It claims to exist, but it's not showing me anything. So who knows why that is, but we've got it here at least. So that's the best we can do. So first I'm going to, oops, I do want an attribute wrangle. First I want to bring it back to its resting position. And I'll just do this at the primitive level, and I'm going to use that, that packed transform we saw before. So I want to get this transform matrix from intrinsic. From this geometry, it's called packed full transform, and I want to get it from the current primitive. And then I'm just going to use packed transform. I'm going to apply it to the current primitive, and I'm just going to give it that inverted matrix. So this is just another way of resetting our transforms, and here we go. I don't know why it disappeared before, but now we have it in the right place. So here we have it sitting in its sort of rest geometry. Now what I want to do is actually use connect adjacent pieces on this thing. It's the easiest way to get constraints that are between adjacent surfaces, and that's really what we want to get. To get the most generalized, correct new constraints, we want to be able to see what pieces are touching each other. So if I want to do that, I'm going to need to unpack this. So I'm going to go to unpack. I don't need to promote anything. I don't need any of that sort of information. All I want here is the geometry. Then I'm going to do connect adjacent pieces. Name is correct. That already exists on that primitive. That's all fine. And I'm going to use adjacent pieces from surface points. So this is going to give me sort of adjacent connected pieces. So if I look at this, I should have sort of one line going between these two pieces, these two fragments I have, and that's exactly what I want. Now you'll see that this has a whole bunch of sort of attributes and things that I don't want on there. It's got the group new piece attribute, but it doesn't actually respect the new piece information that existed up here because I didn't promote it, and so on and so forth. We're going to handle those attributes just in a separate wrangle. So what I really just want to do here is just clean this up, get this geometry keeping only what I want. So I'm going to delete all point attributes except for position. So this little hat says except for. So star says everything. That little hat says except for P and except for name. I want to keep those two things. And I also just want to delete all the groups, just any group, just get rid of everything. So doing this, we're basically just left with this nice clean bit of constraint geometry. There's nothing extraneous on here. This is only what we need, and that's sort of what I want to start with. I'm going to pipe this into an attribute wrangle. And now I just want to copy the attributes from this sort of packed geometry that I actually care about for the next processing. So first I'll find a matching point, find attribval. We just want to match a point attribute called name to the name of this point. So this is just going to find the packed primitive that matches the name on this piece, on this point from the constraint. with that information in hand, we're just going to copy over some attributes from there. So in particular, I want to copy over old name. So I'm going to grab a string. Actually, I don't have to specify that because I'm casting it. It's going to be point one old name match pt. So we're going to grab that. I would like to grab that new piece group as well. So I'm going to go group new piece, and we're going to use in-point group one new piece match pt. So in-point group actually returns 0 or 1 depending on whether or not this point is in this group and this geometry, and group specification is just 0 or 1. So we can just use in-point group to copy over that group value. So now that we've done this, we can see that both have their old name and their group. So all of that is sitting on the constraints now. So the next thing I want to do is I want to set some basic constraint properties on here. And if nothing else, all I really need right now, we're not going to worry about strength because we set that to -1 on the glue parameter. What we absolutely need though is a constraint name. If we don't give it that, then it's not going to treat it like a constraint. So I just want to make sure that this information is on these new constraints we've made as early as possible. I'll just call this set constraint properties. So now these are proper sort of constraints. They'll behave nicely. And the next thing we want to do is filter these, because, you know, at this stage, we just have two pieces, we just created them, so they're next to each other, they have a constraint, that's all well and good. Later on, once things start to break or move around, we're going to want to only keep constraints between pieces whose old pieces used to be attached. So in other words, if there was a broken constraint between, say, piece 0 and piece 1, then we don't ever want a constraint between piece 0 and a fracture of piece 1, because that constraint should be gone. But they may well be adjacent, and in fact they'll always be adjacent to the resting geometry. So we're going to create the constraints in the resting geometry, but we only want to keep the ones that are between pieces that were not already broken apart. So that's going to be the bulk of the next logic bit. Before we even get to that though, I would like to do a group promote, and I want to bring this point group up to primitives. I want to move new piece, and I'm going to rename it and keep the original. I'm going to call it new con. So now at the primitive level, I have this new con group, and what I want to do is delete everything except that group. So this is going to tell me if I've generated constraints in here that already exist in the existing geometry, they're only between old points, they're not between any new points, then I want to get these out of this stream because they'll be kept over here. So I don't want to replace old constraints, I just want to add new constraints. So this will clean those out of there. Now the last thing we need to do is the complicated part, and I've actually sort of copied out my VEX here. I've got it printed so I can type it, and you won't have to sort of labor through me trying to refigure this all out. But I will explain it as I go through. So we want to take, again, this information up here. So we don't want to look at sort of the broken ones. These ones, what we've done here effectively is we've determined in this old stream, we've said, oh, if those names are gone, then get rid of that constraint. But these are exactly the constraints, those old ones, that we want to be able to verify against. So we're going to pull from just this geometry here. So before we've done that filtering. So we're going to use this to compare. And the basic thing we want to do, I'm going to write out sort of some comments here, and actually I'm going to need some more space for this. So I'm going to open up my edit string. So what do we want to do? Well, first we're going to get the points for this constraint. So get constraint points, and that we've seen before. So we're just going to do pt0 is prim point 0 at primnum 0, and pt1 again prim point 0 at primnum 1. So that's all good. We want to get those names. I'm going to go get piece names. And we want to do this a little bit funny. We want to basically say if it's a new piece, get the old name. Otherwise, just get its current name. So we might have a constraint between one old piece and one new piece, so that can happen. In that case, we just want the name of the old piece, but the new piece, we want to know its old name. We actually don't want to know its current name, we want to know what piece it came from originally, because that's what we're going to compare against the existing previous geometry. So we're going to say if in point group, we basically want to find out, is this piece, in the current geometry, we have this group already. If this piece is a new one, then we want to say name0. I should define those. We want a string, name0, and name1. So if it's a new piece, then name0 should be old name for pt0. Otherwise, name0 should be name. And we'll do that for name0, and we'll also do it for name1. So for both points. Just separate those out so we can read them a little bit better. So we want to check point 0, or point 1 rather, name1, point 1, point 1, and name1. Just apply and save. Okay, everything's good. Now, the next thing we want to do is say that basically these names will only be the same if both pieces are new and came from the same parent. We always keep those constraints. So what's going to come in this next block is basically processing to figure out, should we keep this constraint or not? So if these names are the same, then we don't want to even bother with doing that processing. We don't have to. If the names are the same, the only way that ever happens is that they're both new and they both have the same old name. That means that these are the two new pieces from a recently fractured piece. And so we don't even want to worry about those. We're always going to keep those. So what we're going to say is if these names aren't the same, then we're going to do this extra step. So if they are the same, we'll just let them pass through untouched. We'll never delete them. But if they aren't the same, if these are different pieces, they have different names, now we need to check how they respect the existing or previous constraints. So otherwise, what we're going to do first is we want to assume that a link doesn't exist. So let's just set a variable to hold this. And we're going to say exists, so we're going to assume it doesn't exist. So assume no previous link. So what I want to do basically is go through and find everything consistent with these names from the previous geometry. And if there is some constraint in the previous geometry that sort of respects both of these names, then we're going to set exist to 1. We're going to say, okay, that constraint does exist, so we're free to make this new one. When we go through all of those and test all of that, if we've never found a link in the old geometry that respects both these names, then this link shouldn't exist either, and so then we'll delete it. So we're going to assume this is not here. We're going to go through all the options. If one of the options exists, then we'll set exist to 1. So once we exit out, if exists is still 0, then we're going to delete that. So what we'll do at the end here is we'll say if exists is still 0, we're going to remove this prim. 0 at primnum 1. So that's what we'll do at the end. So now we need to do the looping. Now we need to compare against that previous geometry. So first, we want to count. Basically, we want to count all points from existing. I'm going to call this from previous constraints matching name 0. So we're going to start and we're going to find all the points in the previous set of constraints that have the same name as this name 0 we have here. So we'll do count is find attrib val count. We're going to look in geometry 1. It's going to be a point attribute. The attribute is name, and we want to compare it to name 0. If this count is greater than 0, then we can search. So if we don't find anything that matches the first name, well, then we know that there's no constraint in the previous geometry that's going to match, so we don't have to do any of this other work. But if we do find some, now we have to do some remaining checks. So we're going to sort of say for each of those matching points, so this will be a for int I equals 0, I less than count, I plus plus. We're going to loop through all of those points that match name 0. We're going to grab that initial matching point, geometry 1, point, name 0, index I. So we're going to grab that point, so that's the current one that we're processing. And now we need to get all prims using that point. So we found a point that has name 0. To know if this is part of a constraint that attaches to name 1, we need to find the prims that use that point. So this gets a little involved. So to do this, we just have, I'm going to call this PPRMs for point prims. This is an array, and we can just use the function point prims. And this will tell us in geometry 1 what are all the primitives that use this point. And there should only be one. So this seems like we're going to be looping over lots of stuff, but this is really just for generality. There should only be one of these primitives because these points are being generated uniquely. But just in case, we're going to loop through all of these. So for this print, this prim, for each prim in this list, what we're going to do is get all points in that prim. So this is getting very recursive, but basically we found every point that matches name 0, we get every primitive that incorporates that point, and then we're going to look through all the points in that primitive and find if there are any that are name 1. There may be a more straightforward way to do this. This is a little bit brute force, but it does work at the very least. So we're going to do prim points equals prim points, prim points, geometry 1, this prim. And now we're going to say if either name matches name 1, then the prim, let's say then the constraint exists. So now we're just about done here, actually. So this is going to be if string point 1 name PRM PTs 0. So we're basically saying take this first point from prim points, and we're only testing 2 because we know these are constraints. We know these primitives only have 2 points. So we don't need to do a long crazy loop here. We know there's only 2. So we're going to check the first one. We're going to get its name, make sure we cast it as a string. If that equals name 1, or, and we can just copy this whole thing here, if that equals name 1, or the other one equals name 1. We know that one of them equals name 0 by default, because that was sort of how we got here in the first place. So we know one of these 2 points is name 0, so we just need to check if one of the other ones, and we don't know which is which because we don't know what order they're in, but we just need to check that the other one is name 1. And if it is, then we set exists equals to 1. Now, just for the sake of cleaning this up and making it a little bit faster, within this outer loop, so we're going through every primitive that matches name 0, if we find one that exists, we don't have to keep looping through. So we're going to say if exists break. And this basically just says if in one of these previous passes, maybe at I equals 0, we found a match and we had like 5 other primitives that use this point, we can just break out of this loop. We can say, no, don't keep checking, we don't need to. Now that we've done that, assuming there's no errors, and there shouldn't be because I've been copying this code over, there we go. So now we have old constraints, removing ones that involved new points, and then we have new constraints that are only between new points that should have had constraints previously, like before fracturing. So now we just merge these together. And the very last thing I want to do is just clean up a little bit. So I'm going to say group delete, and I'm just going to get rid of these new piece and new con groups. I don't need these here anymore. I don't need these on this geometry. And then we go through to updated constraints. If I do this, it's unhappy here because I don't know why we're in a softnet inside DOPs. don't worry about it. Refresh this, and I believe, yeah, this is currently not pointing in there, so we want to use an external SOP, and we want to point it to what we just created in here, and that was updated. Okay, I have a, I still have these things. Let me get rid of those. What do I call this? Updated constraints. So I want to point this to updated constraints. Accept, and fingers crossed. Okay, so this is partly working. There is one extra thing that we do need to do here, because obviously you can see that these constraints are poking out from everywhere. But what you can also tell is that this block is hanging together. And if we sort of jump out here, you can see that it is fracturing. So it is still coming into these separate pieces, but all these pieces are staying together. So if you don't mind your constraints looking like this, which is ugly, and I don't like it very much, I prefer to have my constraints sort of where they ought to be relative to the geometry. But the fact is, for glue constraints, these offsets don't actually matter. A glue constraint doesn't itself collide with anything, and these are fully sort of linear constraints. So each constraint is basically at an offset to the position or to the piece that it's constraining. That means that these pieces will behave correctly, even though these constraints are sort of anchored to strange places. But the very last thing I want to do is actually clean up these constraints and make sure they're anchored where they ought to be. So, why is this happening? Why are our constraints sitting here? I mean, we did everything right? We made sure our geometry was in resting position when we added these constraints. Shouldn't that make these constraints be in the right place by default? And the problem here is what we've done is we've correctly updated our primitive intrinsics. So all of these prim intrinsics, if we go back to our geometry here, we go to our primitives, all these intrinsics are sort of updating correctly. They're not being reset to sort of 0 or 1 or whatever. But Bullet, it partly uses these, but it also uses, and especially for its constraints, it also uses these point attributes I pointed out earlier. And they're over here. And we have orient, pivot, and rest. So if we go to somewhere where we get some new points, let's even go right back to where we get our first one. So our initial box, it's got a little bit of a, this is effectively 0. So our initial box is not sort of changing in orientation. That's right where we put it. And its pivot and rest are understood as being at 0. That's where that box was created. Once we fracture, what you can see is that pivot and rest for each piece is being set to 0. Everything is being sort of reset to some default here. Orient is all being reset to just sort of basic no change. Pivot is being reset to 0, rest is being reset to 0. If we move forward and get another new point, all these new points, pivot and rest and orient, are being reset. So in the same way that we had to make sure that transforms were respected and sort of carried over, we have to do something about these orient and pivot values. And this is particularly important for where the constraints get displayed, because the constraints understand themselves relative to these rest and pivot transformations. So even though we sort of created our constraints relative to the rest geometry, we never told Bullet what we really mean by that rest geometry. We put it in the primitive intrinsic, so the pieces get packed in the right place, they get simulated in the right place, but we didn't tell Bullet where they were supposed to be at the beginning. And that means Bullet doesn't really understand where the constraints should be attached relative to. So this is a pretty quick fix. We're going to fix it broadly the same way we fixed velocity here. And in particular, orientation, we can just pass through untouched. So I'm going to grab orient, I'm just going to pass that through, and then when we assemble, I'll stick it back on there. So orient is easy. It turns out that our pivot and rest are also really easy. It's just that we can't leave them at 0. And instead, all we have to do here is right after assembling, but before we put this transform, we don't want to move it back to its place initially. Right here, we basically want to update our bullet information. And we want this on the points. So we're going to do a point wrangle, and we're just going to say update bullet attributes. And all we really want to tell it is that our pivot and our rest should be the current points, should be sort of the center of the points where they are right now. And so we can just say pivot is the current point and rest is the current point. And that's actually all we have to do. So now our pivot and our rest, you'll see they're different for the two fragments because they're where the centers of these new fragments are. And this is the information the bullet needs to display those constraints in the right places. So if I refresh this again and we go through, now you'll see those constraints aren't popping up on the outside. We're not seeing them sort of puncturing through. But if I go into wireframe here, you can see all these constraints are inside, right where they should be. And as we tumble down, those constraints are being formed between the pieces exactly where they ought to be. Okay, so at this point we're just about done with everything. If we kind of play through our simulation, we can see that we're fracturing nicely, we're getting constraints being made. What we want to do next is start relaxing this glue strength so that we can actually have these pieces falling apart and becoming separate, because right now we're just keeping everything stuck together. And so we've got our glue strength here at -1, so all we really have to do initially is set this to some higher value here. So I can start with 10,000 here. But if we play this now, we're going to see there's kind of a funny problem that's still here. And it's very easy to fix, but it's something you might run into when you're dealing with constraints. So if we play this, you can see it's fracturing, but then it's continuing to get stuck together, and it's getting stuck together in kind of an unusual way. And this is maybe an interesting effect, but it's not really what we're looking for here. And the problem that's happening, we can see it pretty directly. Let me just go back to an early point here. So here I'm looking at the constraint geometry on this data tab down here. And so we have 4 constraints here. And so you would expect each constraint should have 2 points. So we should have 8 points, but actually we only have 4 points because these constraints are sharing geometry. And if we go down into here and look at that geometry, you can see it right here. Here are our 4 points, and we have sort of 4 or 6 lines between them at this point, I guess. These are the new ones being made here. So if we look at our constraints, we've got 6 constraints here, and they're sharing these 4 points. And this is okay if you're not starting to remove constraints, but what we did in a lot of our constraint removal, when we did remove prim, is we sort of put this 1 flag at the end, which said delete those points as well as the primitive. And so when we're doing this, what we're doing is deleting some of the shared points, and that's starting to scramble some of the other primitives, and everything's just sort of getting wired together a little bit incorrectly when we do that. Now, one solution would be to set these flags to 0 and just get rid of the primitive but not the points it's using. What I like to do instead is actually make sure each of these primitives has unique points, and that way we can get rid of the primitives and the points altogether. And the reason I prefer to do it this way is because with glue constraints, okay, it's fine to have these points sort of rigid and shared here. When you start to move into other constraints, what you often want to do with the constraint is collapse both points to their midpoint. So for hard constraints, for example, and soft constraints, you don't generally actually want to use this rest length, especially in a lot of rigid sims. It just behaves a little bit better when you have a central midpoint. So in those cases, you want to be able to treat each primitive independently and manipulate its points independently. So I generally just prefer for all constraints to make sure each constraint is unique, that all of its points are unique. And we can do that really straightforwardly. Just after we've made our constraints here, all we have to do is drop down a facet node and toggle unique points here. And so if we look at this now, we still have our 5 constraints here, but you can see we have a point for sort of 2 points rather for each constraint. And if we go to sort of our vertices, you can see that we have 6. Each primitive has unique points. So 0 and 1, you'll never see 0 or 1 anywhere else here. 2, 3, 4, we have 1 of each point here. So nothing is being shared anymore. If we sort of go back up here, you can see there's a lot of sharing. So this first primitive, 0, 1, the second one, 0 and 3, then we have 1 and 2, 1 and 3, 2 and 0, 2 and 3, we have lots and lots of sharing here. When we unique, there's no longer any sharing. We have a unique 2 points per primitive, and that's what we want there. So if we just pipe that in here, and then go back up, reset everything. Let me turn off this point view. There we go. Now what we should see is it should fracture apart into multiple pieces here. There we go. And you might wonder, well, where are our constraints now? It just looks like it's fracturing normally. But actually, if we go into wireframe, you'll see that each of these whole blocks is actually composed of fractured pieces. So what we've done is we've added these constraints, but they're also being broken. So we're fracturing dynamically, but we're generating constraints there, but we're still allowing those constraints to be broken as the simulation progresses. So we break once and get that first constraint, but then there's enough force that that constraint breaks, but we shatter these two and they get their own constraints. And as they start to fall apart, you keep getting pieces and constraints and breaking all at sort of the pace that you like. So hopefully this has been useful for you. You've learned some sort of new workflow bits. There's a lot of kind of new bits in here that you might not have seen before, things like applying a new data container, things like putting the constraints inside of the geometry here instead of sort of leaving them as a relationship, and that lets you sort of modify these solvers over here. And the basic workflow and the things to remember, if we just walk through our network here, the main thing is to do this pre-transform back into the resting space, do your fracturing in that resting space, and then reverse that transform afterwards. And if you do that, you'll have everything behaving nice and cleanly. So you just want to reverse that primitive intrinsic, and you want to modify those bullet variables, pivot and rest. And if you do all of that, then you'll end up with your geometry nice and well behaved, and you'll be able to sort of put it back in its resting state, and everything will behave just nicely. So if we look back here, we can see all this fracturing occurring right at that resting state. So thanks very much for watching. I know this has been a long one with sort of a lot of sort of moving parts. Hopefully you've been able to get some useful tidbits out of it. As always, if you have any sort of questions or comments, please drop me a line. I'm going to try to make this HIP file available so you can sort of take a look through it and see how this all kind of comes together in case you sort of missed some parts in the tutorial. And if you have any suggestions for other tutorials you'd like to see, by all means, please let me know. Thank you very much, and goodbye.